All right, let's go ahead and get started. The videos, both of them for Tuesday's lecture, are up on the MediaSpace site and the Echo 360 site. I just haven't had a chance to put the link on the main page. And I have written up an example of actually using the Mon stuff to speed up a dynamic programming algorithm, which will be in the notes that I'll post within an hour after class. They're written up and ready to go. I just haven't had a chance to upload them today. I don't think there are any administrative announcements except that we are having a little bit of administrative trouble actually hiring the graders. Something about nobody getting any raises and someone working for X dollars last semester and working for X plus $1 this semester is counted as a raise, even if it's a different class. I'm hoping that we'll be able to get that straightened out in the very near future, but there may be some delays in getting homework 1 back to you. I'm hoping we can just double team homework 1 and homework 2 and get caught back up. But I want to warn you that we're experiencing some troubles on the administrative back end that we're trying to address. So Tuesday was the last dynamic programming lecture. We are now through one of the 4 major chunks of the class. The second chunk of the class, I'm shifting gears a little bit. This chunk of the class is mostly going about applications of randomness. Why did you do that? Okay. Why did you do that? Okay. Randomized algorithms, in particular, algorithms that incorporate randomness as one of the components of the algorithm. And I want to start with what I think is one of the simplest but most telling examples where randomness is helpful. And this is a problem that was proposed around 1990 by a computer scientist named Jeffrey Rollins, who innocently wrote this into his textbook. And it actually turned out to be a really beautiful illustration of the power of randomness. So I want you to imagine that you're in a machine shop that produces nuts and bolts of various sizes. And in particular, you've taken your sample cart out to go on the road, and you've got in your sample one nut and one bolt of every size that your company makes. But in your disorganization walking out the door, you forgot to match them up. Now, I actually went down to Home Depot a decade ago and bought every nut and every bolt they had. And in this case, it's actually relatively easy to match things up because you can just sort of eye the sizes. But I'm going to impose a somewhat artificial constraint. I want you to imagine that the sizes of these objects are so close together that if you pick up two bolts, you actually have no way of comparing them. You can't tell whether one of the bolts is bigger or smaller. Similarly, if you pick up two nuts, you really have no way of knowing which one of these is bigger or smaller. But what you can do is pick up a nut and a bolt and try to put them together. And you'll discover either that the nut is too small, or the nut is too big, or if you're very, very lucky, no, I wasn't. If you're very, very lucky, yes, the bolt will screw on and stay tight. Okay? Now, you're allowed, in other words, to pick up an arbitrary bolt and an arbitrary nut and try to match them together, and you have three possible outcomes. The bolt is bigger, the nut is bigger, or they're the same size. And now your task is to match everything up. Okay? Now, if you think about this for a little while, you'll come up with the brute force solution. Pick up a bolt, test it against every nut until you find the one that matches. Pick up the next bolt, try it against every nut until it matches. For all nuts, for all bolts, try that nut against that bolt. A simple quadratic algorithm. Okay? Now, I will tell you that there is an algorithm that can solve this problem where the number of tests is big O of n log n. And the reason why you might expect there to be an n log n algorithm hiding in here is that if you could somehow magically sort the bolts in order from smallest to largest, then you could take an arbitrary nut and do a binary search to figure out the matching bolt. Or if you sort the nuts and you sort the bolts, then they just match up automatically. But you can't, apparently, sort the bolts because you cannot compare two bolts directly. You're only allowed to compare bolts to nuts. You can't compare two nuts directly. You're only allowed to compare nuts to bolts. This textbook came out was proposed in 1990. In 1993, someone proposed an algorithm, the first algorithm. It took 3 years for a team of people at Berkeley to propose the first subquadratic algorithm. I believe it ran in n times log n to the fourth, so log times log times log times log. And then a year and a half later, there was another algorithm that ran in time n log squared n, so n times log n times log n. And then a few years after that, there was a proof that an algorithm exists that uses n log n comparisons, but we don't know how to write it down. And then a few years after that, somebody finally figured out how to construct. There's a combinatorial object called an expander, which nobody knew how to build, but we knew that we knew they existed, but we didn't know how to build it. Somebody finally figured out how to build it, which meant that there was an algorithm that could get by with only 3,000 times n log n steps. And then over time, as the construction of expanders got better, you roll, okay, I need to pick up bolt 8. Okay. Now, there are culturally, there's a different way that people like to talk about this, which is, well, for quicksort, well, if I assume that the data is given to me in random order, then quicksort runs in n log n time. The problem with that viewpoint is the data is not given to you in random order. And even if it was, what you actually mean is every permutation is equally likely. And every permutation is not equally likely. So, have any of you taken a machine learning class? A statistical, or are any of you taking a machine learning class that meets right now over in Siebel? One of the key problems in machine learning is you're given a sample from some probability distribution, and you want to figure out what that probability distribution is. If you could just assume that the data is generated uniformly at random, hooray, we've solved machine learning. It's uniformly at random. We can go home now. It's not, right? But you can make the order uniformly random by having the randomness in the algorithm itself. You don't trust the world to be random in exactly the way you want. You impose the randomness on the data in exactly the way you want. You take control of the randomness and you change the order yourself. The world is not going to be nice to you. It's a horrible, ugly, evil place that's out to get you. It's out to make your code crash or run, be incorrect, or at least run for a very long time. And you have to write your code as though the world is out to get you. But you can, if you want to use the assumption that when I pick up a bolt, I'm picking it up at random, then you have to write into your code, choose a random bolt. And this is what it means for the algorithm to be randomized. That I'm not assuming anything about, I'm not assuming that my data is random. I'm not assuming that the order of my data is random. I'm assuming worst case behavior. I'm still assuming the universe is out to get me. But I'm using randomness to kind of defeat the all-power adversary that's trying to screw up my code. Right, so let me say this in a little bit more detail, formality, exactly what we mean. Okay, so there's this sense that you can have, you're interested in an algorithm A, which you will run on some input X, and it will have some running time. Right? So this is time for algorithm A on input X. Now, normally when we analyze algorithms, because we think the world is out to get us, because we want to always be able to say this algorithm with no other assumptions always runs in, say, less than n squared time, what we're actually interested in is the worst case running time of the algorithm as a function of the input size. Right? So this is the maximum over all inputs of size n of the running time of the algorithm on that input. This is worst case. Now you will still occasionally see in some old algorithms textbooks or on Wikipedia people talking about best case analysis. Nobody cares how fast your algorithm is in the best case. Because you can always engineer an algorithm to say, is the input all 5s? Then output the right answer. And then in the best case, the algorithm runs in constant time. Okay, we're done with that. That was best case algorithm design. What we want is to design an algorithm that we can guarantee is always fast, which means no matter what input we feed in, it's going to be, the running time is going to be less than t of n. Now, the standard notion, the intuitive notion of average running time is that you take the expected value over some distribution of inputs of size x of the running time on that input. And this is a perfectly reasonable, well-defined notion, but it's absolutely useless in practice, because in practice we don't know what that distribution is. If we don't know what the distribution is, then there's no way that we can make any predictions about the behavior of the algorithm by applying this tool. Right? On the other hand, if A itself is randomized, which means in one of the instructions that the algorithm is allowed to execute is flip a coin. If it came up heads, do this. If it came up tails, do that. Roll a die. If it came up a 1, do this. If it came up a 3, do that. Roll an m-sided die, and depending on what number came up, put the data into the array at that address. Hashing. Okay. But then the running time for the algorithm on a particular input is no longer just a number, because running the same algorithm on the same input might give you different results. It's a random variable now. It's not deterministic, and it's explicitly, intentionally not deterministic. And so you really need to be thinking about, the simplest statistic that you might imagine for any random variable is what is its expectation? What, if I run this algorithm on this input many, many times, what is the average going to be for the running times? But then, again, I'm not interested really in the behavior on a particular input. I have to consider all possible inputs of a certain size. But I'm not going to let the input itself be random, because I can't assume that. I have to come up with some sort of prediction that this algorithm, I expect this algorithm to run in this time no matter what the input is. And so the right way to do this is to take the max over all inputs of a certain size of the expected value of the running time on that input. This is what is known as worst case expected running time. Or often we'll leave out worst case, just as we normally leave out worst case when we're talking about the running time of deterministic algorithms that always behave the same way. And so when I'm thinking about randomized algorithms and I want to know what the running time is, this is the metric that this is how I'm trying to analyze the algorithm. The universe is horrible to me. It chooses the absolute worst possible input, but then once the input is given to me, the algorithm can make random choices, and I average over, if you imagine every random choice splits off a parallel universe, I average over all parallel universes the behavior of the algorithm. The data is worst case, the algorithm is random. And if it just so happens that you know something about the distribution, then you can improve this analysis. You can put another E on the outside that's, if you actually do know the distribution, you can improve this analysis. You can often put tighter bounds. But that's really not a topic for this class. This is more a topic for, say, a machine learning class. Okay. So this is what we're going to try to do, and what we're eventually going to lead up to is the statement that quicksort has worst case expected running time, big O of n log n if you always choose the pivot at random. Meaning, if the algorithm explicitly, intentionally chooses the input at random. Now, in my model of computation, I'm going to assume that I have access to a subroutine returns an element of the set from 1 to k uniformly at random and independently. In other words, this is random of 10, right? This die that I'm holding in my hand, I've got a bunch of random of 10s. Here's a random of 4. In other words, it's exactly what you would expect from rolling a fair k-sided die. Flipping a coin is calling random of 2. You either get a 1 or a 2. And you can later map those onto 0 and 1, or true and false, or Democrat or Republican, Bernie or Hillary, or whatever you want your random choices to be. But I'm just going to model the random choices by saying, for any positive integer k, I can generate in constant time a number between 1 and k chosen uniformly at random. Okay. By the way, in case you weren't watching the news carefully in Iowa, Hillary won slightly more votes than Bernie, but only because in certain districts in Iowa, the actual vote tallies were ties. And so because of local election laws, those districts were decided by flipping a coin. Okay, so this happens in real life. All right, so let me go back to the nuts and bolts problem, but rather than going directly into matching up all of the nuts and all of the bolts, let me think about the simpler problem. I just want to find one match, one matching pair. Okay, I don't care which one, just find me a matching pair. Okay. Now, the obvious deterministic algorithm is I pick up a bolt, I don't know which one I'm getting, and then I try all of the nuts until I find a match. Okay. If I'm a little bit more clever, I recognize that I only need n-1 tests. I don't ever actually need to do n tests, where n is the number of nuts and the number of bolts. Why is that?
Once you've tried n-1, you know the last one has to be it.
Right. I'm given as a condition of the problem that there is a match. And so if I've tried n-1 things and I haven't found a match yet, then the last one must be a match, and I know that even without doing the test. Okay? So, let me try doing this randomly, so randomized. So the randomized algorithm is pick a random bolt, and then for I goes from 1 to n, try try if match return I, and at the end return n. Okay, so the randomness that I'm going to put into the algorithm is in the first line. I'm going to roll an n-sided die, and that tells me which bolt to pick up. In practice, I throw the bolts into a bag, I shake it, I hold it behind my head, and stand on one foot, pull it out with my non-dominant hand. Okay. Intuitively, what would you expect the behavior of this algorithm to be?
It breaks.
Sorry?
I mean,
The only thing that I have done that's actually different from the deterministic algorithm is this line, that word. The deterministic algorithm just omits the word random. Okay, so it's still correct. I'm just being a little bit more specific about which fault I want to pick, namely everyone with equal probability. So what would I expect? What do you think the expected number of tests is going to be? Yeah. So I'm hearing exactly the same. I'm hearing n over 2. Any other guesses? So neither of those, but n over 2 is closer.
1 over e.
1 over e. Excellent guess. Wrong problem. Okay. Maybe later in the semester we'll talk about hiring secretaries. What the heck? I'll just tell you the problem. Your job is to hire a secretary. There's a line of people going out the door who are applying for the job. You're going to interview them one at a time, but immediately after the interview, you have to decide either to make that candidate the offer or not. What is assuming that you get to randomly permute the line of people coming in before the interviews, what's the optimal strategy for hiring the best person? So if you think of it as, I want the tallest person, but I've randomly permuted and I only get to, they come in, oh wow, you're tall. But maybe there's somebody taller and further out. The optimal strategy turns out to be that you invite one at a time the first 1 over e fraction of the people in line and say, no, I'm not hiring you. And the next person you see who's taller than any of those n over e that you've seen earlier, that's the person you hire. 1 over e. Okay, yes?
Is it log n? Because you're multiplying the probability of it not being the right one by n minus 1 over n?
So the question is it log n? And really the question is it something involving harmonic numbers? We'll see the harmonic numbers, but in this case, it really is going to be about n over 2.
N minus 1 over 2.
Okay, good. So it's a little bit better. It's actually going to be a little bit closer to n minus 1 over 2, but even that is not quite exactly right. Now, of course, if we're really only interested in, big O bounds, it's still big O of n. So it turns out that, not the right pen, the expected number of tests is exactly n plus 1 over 2 minus 1 over n. Okay, of course. So how do I actually see that? So I'm interested in the expected running time. In this case, I don't really have different inputs of size n. I have n nuts and n bolts, and it's the same. So I don't have different x's to try. The max part of it isn't that interesting. So I can look at just one of the ways of defining expectation is that I sum over all possibilities for the number of tests of t times the probability that my running time is actually t. That the probability, if I knew the probability that the algorithm performed exactly t tests, I could plug it into the summation and then do some math, which we all know how to do. Namely, Google for Wolfram Alpha, plug it in. Okay, so, but in principle, we'll end up with something that we know how to solve. The only question is, what is that? What's the probability that this algorithm performs exactly t tests? Well, let's start by thinking about What's the probability that T of n is equal to 1? 1 over n. Because I chose my bolt at random, and so I'm equally likely to choose any bolt. In particular, I have the same likelihood of choosing the bolt that matches not 1 as any other bolt. And so that probability is 1 over n. What's the probability that T of n is equal to n?
Fails n minus 1.
Yeah, I heard somebody say the right answer. 0. The algorithm always runs in at most n minus 1 tests. Right? It's the same algorithm, but I just, so it's never n. So the answer here turns out to be this 2 cases. Okay, there are 2 ways for the answer to be n minus 1. Either the random bolt that I pick matches the second to last nut, or it matches the last nut. In either of those 2 possibilities, the algorithm will perform exactly n minus 1 tests. But the probability, let's say n is big, the probability that T of n is equal to 5, this is the probability that the bolt matches nut 5. But I chose the bolt uniformly at random, so the one that matches bolt 5 had the same chance of being chosen as any other. So its probability is 1 over n. Okay. So at this point, I can do some math. I can plug this expression into here. I can do the algebra, and I'll get n plus 1 over 2 minus 1 over n. If you want to see the algebra, you can look in the notes. Okay, yes?
Are you replacing the bolt or taking it out?
No.
So
There's only, I pick one bolt, that's it. There's only one bolt throughout the entire algorithm.
oh, so you're not just doing the nuts at random, it's just the bolt.
Right. The only randomness is I pick up a bolt. Yes?
How do you get a 2 over n when t equals 2?
Okay, how do I get a 2 over n here? I have the same number of tests if the bolt matches the second to last nut, nut n minus 1, or if it matches the last nut. Because I don't actually have to do the test against the last nut. Remember? Okay. So, I would, and generally, another way that you can see this is, if I didn't have this stupid trick at the end of avoiding the last test, every number between 1 and n is equally likely. And so I would expect the average to be halfway between 1 and n. But 1 over n of the time, I get to save 1 test. All right? So this is a simple example of the kind of thinking that we need to be able to do. We're ultimately thinking about the probabilities of certain events happening in the algorithm because the algorithm has made these random choices. Okay. Now, I can apply this randomized algorithm in a for loop, and I find one match, and then I run it again, and I find another match. And I'm still going to get something that runs in about n squared time.
Shouldn't the first case be like 1 over n minus t? Because you take 1 out, right? Just like
What's the probability that this will match nut number 1?
1 over n,
What is the probability that this will match bolt number 17?
But you throw away.
What is the probability that this will match bolt number 17? 1 over n. All right. And this is one of the tricks to thinking about the way that randomized algorithms work. If you try to stack up the probabilities and say, well, 1 over n time I get a match and then I don't, you can do this, but what's going to happen is you say, well, what's the probability that t of n is equal to 3? Well, I didn't get a match on the first choice. And I didn't get a match on the second choice. Or sorry. And I did get a match on the third choice. Oh, look. 1 over n. Right? So, I mean, there are multiple ways of thinking about it that eventually lead to the same answer. And so part of the trick of doing the analysis is figuring out the way that gets you to the answer fastest. And that often means not thinking about the algorithm in terms of its progression from one state to the next, but rather under what conditions will it exhibit this behavior. All right. So let me go back to matching all of the nuts and all of the bolts. And people have already sort of thrown out the answer that Rollins was proposed, which is the following. I'm going to match n things. So I'm going to pick a random bolt. And again, that's important. Split the nuts into, let me call this random bolt B. Smaller than B, matches B, greater than B. Okay? And I do that by taking each nut and comparing it to the random bolt B that I've chosen. Now, one of those nuts is going to match B exactly. So now I'm going to split bolts into smaller than n and bigger than n. And I've already found the one that matches n, so I don't actually have to do that test. And now I'm going to recursively match all the nuts that are smaller than b with all the bolts that are smaller than n. And I'm going to recursively match all the nuts that are bigger than b and all the bolts that are bigger than n. Okay, so I found one match here. When I recurse on the smaller things, I'll find all the matches there. When I recurse on the bigger things, I'll find all the matches there. Now, one thing to verify is that, in fact, every bolt in this set less than n has a matching nut in this set less than b. Right? Think about this. This just follows from the axiom that for every bolt there's a matching one, and the way the comparisons work. So this is, in fact, a recursive call to a set of nuts and a set of bolts that have the same number of each kind of object, and there is a match between them. So I can properly hand this off to the recursion fairy. Similarly for the bigger size. This is very slightly more complicated than what you would normally do for quicksort. The way quicksort normally works is you pick an element of the input array, called the pivot, randomly. You split the rest of the array into the stuff that's smaller than the pivot and the stuff that's bigger than the pivot. And then you recursively sort the small stuff and you recursively sort the big stuff. So what we're really getting at here is the analysis of randomized quicksort, but it just so happens that you can apply it with very minor changes to this nuts and bolts problem. Now, the non-recursive part of the algorithm, which corresponds to the partition phase of quicksort, I need to do some number of tests. Can anybody guess how many tests this is going to require? This part of the algorithm is deterministic, so there's an actual answer. It's not a random thing at all. Somebody over there said it. You want to say it louder? 2n minus 1. Because I compare b against all n nuts, and then I compare n against all of the bolts except b. Well, I could cut that down a little bit. because if I actually, because I've chosen a random bolt, there is some small probability that the last nut that I would compare B to is the one that actually matches, and I don't really have to do that match, so I can shave off. Okay, fine. This is more optimization than I want to do. Let's just not play that little -1 over n trick, and just say this is 2n minus 1. Okay. So what this means is I now have a recurrence for describing the expected running time of my algorithm. Okay, the expected running time, I'm just going to write a bar over here instead of an E because otherwise this is going to get really messy. I'm always going to run 2n minus 1 tests, and then let me call the number of nuts and bolts in the first recursive subproblem K. Actually, let me say that suppose the bolt I pick is the kth smallest bolt. So there are k minus 1 things that are smaller and n minus k things that are bigger. And these are also random. So those are expected running times, except I don't know what k is. And if I didn't choose the pivot at random, I would have to put a max over all possible k here. But I'm not just arbitrarily choosing a pivot, I'm not arbitrarily choosing a pivot bolt. I'm explicitly choosing a bolt uniformly at random, which means now I can have an expected value here over all choices of k, where implicitly I mean this k is chosen uniformly at random between 1 and n. Now, I am doing one thing that's playing a little bit fast and loose here, which is how do I know that I can take this expected value and factor it into, well, there's this part of it which I can just add, and then there's this part of it which I can treat completely independently, and that part that I can treat completely independently. And I can average over this. Ultimately, this boils down to one of the most useful rules about probability: linearity of expectation. Okay, the expected value of x plus y is equal to the expected value of x plus the expected value of y. Now, in this particular case, it turns out that these two random variables are completely independent from each other, because I have over on the left, my left recursion fairy has her own set of random bits that she generates, and over on the right, my right recursion fairy has a completely independent set of random bits that she generates as well, because I said in the definition of random that these are independent. So in this particular case, it happens that these subproblems are independent in the probabilistic sense, but that's not necessary for linearity. So in particular, if I take a 20-sided die, opposite sides of this die, the numbers always sum up to 21. Just like on a 6-sided die, the opposite numbers always sum up to 7. So I could take as my random variable x whatever number is on the top of the die when I roll it, in this case 17, and I can take as my variable y whatever number showed up on the bottom, in this case 4. And these two random variables are not independent. They're once you know what the value of x is, you absolutely know what the value of y is. Nevertheless, I can say, well, every number between 1 and 20 is equally likely, so the expected value of x is 21 over 2. The expected value of y is 21 over 2. And so the expected value of the sum is 21. So no matter how I roll the dice, the expected value of the sum of the face on the top and the face on the bottom is 21. Well, of course it is, because no matter how the die lands, the top and bottom faces sum up to 21. Okay? And this linearity is one of the big important tools that we use when we're analyzing algorithms, because we want to factor ultimately what is a count, a sum of how many things happen in this part of the algorithm versus how many things happen in that part of the algorithm, and be able to analyze them separately, even though they might depend on the same random numbers. Okay? All right. Now, if you're Bob Sedgewick, you are getting a PhD in computer science in 1976 at Princeton. You can solve that recurrence. I'm being a little bit unfair. He did more than solve the recurrence. In particular, he did more than, but Bob Sedgewick's thesis was about the behavior of randomized quicksort. And so he not only figured out the expected running time, but also the variance of the running time and a few other things. Also for several variants of quicksort, like what happens if I choose 2 pivots and partition into 3 parts, or I choose 3 pivots and take the median and use that to partition. And the way that he did it was he took this recurrence and he turned that expected value into a sum, and he did a bunch of algebraic manipulation, which, if you really care, looks like this in the notes. But I want to give you at least first a piece of intuition and then a more formal analysis that actually works and that I can actually keep in my head. Okay. So, the goal for, maybe arguably one of the reasons why with quicksort we'd like to choose a pivot that's kind of in the middle is that we like to split the subproblems into kind of smaller parts. Because as long as we make both parts smaller by some constant factor, the recursion tree will have depth only log n. It'll be kind of balanced. It won't be exactly balanced. But even if I manage to split into, say, n over 3 and 2n over 3, or n over 10 and 9n over 10, in the analysis of the resulting recurrence, I'm going to get a tree that has n work at every level, and the depth is going to be some constant times log n. Okay? So I like pivots that are kind of in the middle. All right? So let's define a good pivot. Which I can't spell, is one where I'm in the middle half. A good pivot is one where when I run the algorithm, the small subset that I recurse on has at least 1/4 of the remaining nuts and bolts, but no more than 3/4. And the large set has at least 1/4, but no more than 3/4. I'm going to be fuzzy about whether this is less than or less than or equal to. It doesn't really matter. And I'm going to say the pivot is bad otherwise. Okay. Otherwise, I don't know what letter that is. Okay, but I've chosen this definition of good and bad because what I really want my definition to be is the probability that pivot is good to be about 1/2. Now, there's going to be some issues with floors and ceilings, but keep in mind that I'm just trying to show you intuition, and what I'm giving you is not a formal proof. Okay. So, let me take this recurrence. Didn't need to do that. Okay. And see if we can write it slightly differently. Well, let me be conservative about this. If the pivot is bad, and I'll detect this in the algorithm, I'm going to make a small change to the algorithm. If the pivot is bad, I'm just going to say, oh, crap, start over. Start that recursive subproblem over. Okay? So half the, and this is making the algorithm slower, so I need to put a less than there. So half the time, I'm just going to start over. Okay? The other half of the time, when the pivot is good, well, to be conservative about this, again, with an upper bound, I want to think about what happens when I have the worst possible good pivot. Which is what? N over 4. I mean, things are slow when they're, even if I'm trying, between different good pivots, if I split things exactly in half, I'm going to get a shallower recursion tree than if I split things 1/4, 3/4. So the worst pivot I can hope for is, again, ignoring floors and ceilings and -1s, n over 4 plus bar of 3n over 4. Now, this is a really kind of strange recurrence because I have, this function t bar of n over here on the left, and I have the same function t bar of n over here on the right. Fortunately, I can do some math. Okay, good. And actually, that half bothers me a little bit. So let me just write this down somewhat differently. 4n minus 2 plus t bar of n over 4 plus t bar of 3n over 4. And now, okay, this is big O of n. Now I have a recurrence which I can solve using the standard recursion tree argument. I have a tree where at the roots I do, 4n over 2 work. Let me just abbreviate that. And then on the left side I do n over 4, and on the right side I do 3n over 4, and so on. And then at every level of the tree I'm doing n work. And the depth of the tree is, it turns out to be log base 4/3 of n because on the right side I decay slower than on the left. So this will eventually decay down to something of constant size, which I can solve by brute force after roughly this many pieces, this many levels. And so the running time of my algorithm, what is that? What just happened? Is n log n. Okay? So that's an intuitive argument for why this random choice of pivot bolt gives me an expected behavior of order n log n tests. With a constant that is, I don't know, what is log base 4/3 of 2 times 4? It's about, 6. Remember when I said the deterministic algorithm, the best deterministic algorithm we know for this runs in like 50 n log n? And we did something, back of the envelope, really loose, and we got something like 6 n log n. Just by doing things randomly. Okay. And I actually successfully explained it to you in 45 minutes. Okay. Using only tools that you already knew. Right. Now there is a problem with this, which is, there are a couple of minor problems with this argument with the plus and minus ones and floors and ceilings. Those are actually turn out to be relatively easy to fix if I want something formal. The more difficult piece of the argument is the assumption that the worst possible good pivot is this one. n over 4 to 3 n over 4. And this turns out to be true, and you can see that it's true if you believe that the answer is n log n, because you make an argument that n log n is convex. It's a function that slopes up, and the second derivative is positive, and you argue about second derivatives and what that means. But then I'm using the convexity formally to make that worst case assumption, and then I'm using the result of that analysis to prove convexity. It's kind of circular reasoning. And if I work very hard, I can untangle that reasoning by using induction, but at this point I'm just solving the original recurrence. Yeah, okay. So I want to come up with a different way of thinking about the behavior of the algorithm that will allow me to get, in a formal sense, get straight to the expected running time. Which means, for once, I'm actually going to not think about the algorithm recursively. Okay? I'm going to abandon my normal stance, which is your goal when you're thinking about a recursive algorithm is make things a little bit simpler, and then it's not your problem anymore. And that's really useful when you're normally designing randomized algorithms. Or sorry, when you're designing recursive algorithms. But I'm going to step in and think of the behavior of the algorithm in a more global sense. And I really want to think of it this way. What is the definition of the running time of the algorithm? This is the number of times I test any bolt against any nut. So let me write that formally. Okay, I number the bolts from 1 to n, I number nuts from 1 to n, and now you run the algorithm, and every time you test any bolt against any nut, I give you $1. Now you're not, because I know you want dollars, but you also want to get out and be done, so you're trying to minimize the amount of money you make for some reason. Maybe every time you test a nut in a bolt, you give me $1. Okay. Now notice that you're never going to test a nut against a bolt more than once. Right? First, in fact, the algorithm as I wrote it never does. But at a more philosophical level, once you've done the test, you already know the answer. You could just memorize it. And then instead of actually doing the test, you say, oh, did I already do that? Okay, good. And that doesn't count as actually testing that. So it's either 0 or 1. And so again, that bracket means 1 if you do the test and 0 if you don't. And now I ask for every nut and every bolt, when the algorithm finished, did it test this pair of objects? And I sum all those up. Okay. But now remember, I'm interested not, in a particular run of the algorithm, but rather the expected behavior of the algorithm. Okay. Remember linearity of expectation? The expected value of a sum is the sum of expected values. So I want the expected value of this 0, 1 variable. All right, let me quickly go on a diversion here. If I have a variable that's either 0 or 1, its expected value is 0 times the probability that x is equal to 0 plus 1 times the probability that x is equal to 1, which can be simplified So what I actually want to write here is probability. Okay, so the expected running time of my algorithm is the sum over all nut-bolt pairs of the probability that I compare the nut I against bolt J. Yeah, the other way around. Turns out not to matter. Okay? So what I'd like to be able to do is sort of step back and say, let me decide for an arbitrary I and J if I can figure out the probability of comparing that pair of arguments. Okay? So I want you to imagine for the moment that for purposes of analysis, I've lined up the nuts and the bolts in sorted order from 1 to n. Now, of course, I don't really know the sorted order in advance, but I'm doing a post-mortem analysis of how the algorithm behaved. Okay, and then I'm going to pick a particular bolt I and a particular bolt nut J, and I want to know what's the probability that I compared those two objects. All right, so maybe as a sanity check, let me consider the easy special case. I and J are equal. Okay, so what is the probability that I test bolts, no, not one. I test bolt I against nut I. It might help to look at the algorithm. One, you will always test every nut against its corresponding bolt. Is that circled line? Always, because I didn't do that weird optimization thing, right? Okay, so in the third line of the algorithm, I will test the pivot bolt against the matching nut. Oh, wait, I forgot something in the algorithm. What's the base case? What's the simplest base case you can think of? Nothing. There ain't nothing to do. I've got a set of 0 bolts and a set of 0 nuts, and I want to match them up. Done. Okay? But what that means is, if I use the empty sets of my base case, at some recursive level, somewhere in the tree, every bolt gets to be a pivot. Which means every bolt is going to be tested against its match. Okay? Okay, so in this case, the answer is 1. All right. Let me think of another interesting case here. Let's suppose that I is equal to 1 and j is equal to n. Okay. What is the probability that I'm going to compare the smallest bolt to the largest nut? You're close. So there was a suggestion the answer is 1 over n. Why would you say 1 over n? Or does somebody have another hypothesis? 2 over n. Why 2 over n?
Because you only do the comparison if you pick the smallest bolt of the largest bolt is the first one.
Right. So the question is, first of all, the algorithm is going to choose a pivot. The pivot bolt is equally likely to be any one of these n bolts up here at the top. If the pivot bolt I choose is somewhere in the middle, then I'm going to end up splitting the subproblem into things smaller than the pivot and things larger than the pivot. And I and j are often independent subproblems. They will never see each other. They will never talk to each other. They will never be compared. But if the pivot is 1, then this bolt is the pivot bolt, which means it's compared to every nut. In particular, it's compared to the largest one. On the other hand, if the pivot is the largest bolt, I'll compare it to every nut, and in particular, I'll find the match that's the largest nut, and then I'll take the largest nut and compare it to every other bolt, in particular, the bolt number 1. Okay? So there are 2 choices for the initial pivot that lead to testing that particular pair of objects. And so the answer to what this probability is 2 over n. Okay. Now let's see if we can figure out what happens in the general case. Okay, so I is somewhere here in the middle. J is somewhere here. Hopefully it's clear that swapping I and J doesn't make any difference, so I'm just going to assume I is less than J. And now I need to choose a pivot. If I choose a pivot that's between I and J, then I and J will wander off into separate universes and never talk to each other again. If I choose a pivot that is smaller than both I and J, I really haven't learned anything. I and J wander into the same subproblem on the right. Similarly, if I choose my pivot to be larger than both of them, the I and J both wander over to the subproblem on the left. The event that prevents I and J from being compared is at some point in my recursive algorithm, I choose a pivot strictly between I and J. And that sends I off to the left and J off to the right. But I do that before I choose either I or J themselves as pivots. Okay? So I'm going to test I against J if and only if the first pivot chosen from the set I plus 1 up through J is I or J. Okay. This takes some time to sink in because what I'm basically claiming is the only recursive subproblem that matters is the one that either splits I and J or tests I and J against each other. I'm sort of ignoring the fact that I've got this huge tree of problems, except to observe that if I choose a pivot in between before I choose either I or J itself as a pivot, then that's what prevents me from doing the comparison. So, if you like, I can argue this inductively. So, suppose that the first pivot I choose is bigger than both I and J. In that case, I am left with a subproblem where, by the induction hypothesis, I and J are tested against each other if and only if the first pivot I choose between in that range is either I or J. Right, so the induction hypothesis applies because I've got a smaller subset. Similarly, if the first pivot I choose is on the left, the induction hypothesis implies this characterization. If the first pivot I pick is in the middle, strictly between I and J, then I don't compare I and J. They went off to each other's subproblems. If the first pivot I pick is I, then I do the comparison. If the first pivot I pick is J, then I do the comparison. And so in each of those 5 cases, I have this equivalence. 2 of the cases by induction, 3 of the cases by direct case analysis. Okay? So, what is the probability then of testing bolt not I against bolt J or vice versa? This is 2 over J minus I plus 1. And just to be on the safe side, because I implicitly assumed I was less than J when we went through this, really I need to put absolute values here. Okay? Now let me go back up to the top. I have a sum over all I, sum over all J of that. Yes?
It's only true if I and J aren't equal, right?
No. Oh, yeah, okay. If I and J are actually equal, then that should be a 1. Okay, yeah. There's some off by 1s in there, which you can adjust for. Okay. But if I want to give it a sort of hint of what this algorithm looks like, I'm going to have n different pairs where the value is 1. And then it turns out that if I and J are adjacent, you're also going to get a probability of 1. Okay? So if I just consider I less than J, again, I'm going to have n minus 1 pairs where the probability is 1. And then I'm going to have n minus 2 pairs where the probability is a half. And n minus 3 pairs where the probability is a third. And so on. So I do this more formally in the notes. What is this? Right? This is a sum that eventually is going to go down to 1 over n. This summation is called the nth harmonic number. I mean, this is the sum over all I from 1 to n, 1 over I. Right? It's about the natural log of n plus 1. Okay? Every one of these columns, I mean, I actually have a sort of triangular things, which h of n plus h of n minus 1 and so on. But if I'm being conservative, I just fill out the whole rectangular array. And so I get h of n times n, which is n log n. Okay? Yes. I see somebody making the appropriate hand motions. Jazz hands. Right? Now, if you want to do this a little bit more formally, that should be not 1, 1/2, 1/3, but 1, 2/3, 2/4, 2/5, and so on, and you actually get 2 h of n down here. If you actually go through the formal analysis, what you end up with is 4n times h of n minus 7n plus 4 times h of n. This much algebra. Or you can ask Wolfram. Okay. So what you end up with is 4n times the natural log of n. That turns out to be about 5n times log base 2 of n, which is normally what we think of log when we're talking about algorithms. Okay. Otherwise, except for the algebra, I've actually shown you everything. You can trust me that I've done the algebra correctly, or you can go read the notes and not trust me. Always the better choice. But you actually get something with a relatively small constant here. Any questions? Okay, thank you.